applications of trig equations. Tends to be a little bit easier than this, so we move on to 8.6. There are no questions in 8.5. No questions, okay. Usually that's a hard section. And a lot of students have questions, but applications of trig. Everyone's good with that? Okay. Applications of trig. So most people, I guess, someone said they're good, so that's good to go. So. Okay, so we can kind of move on to the applications. The applications here are relatively basic and easy. It's just all about solving triangles. So we're just going to look at some simple applications. And I'll show them in the textbook. And these simple applications are all about essentially what we did in the previous sections, solving triangles. And they're either going to be right triangles, there's some right triangle problems, as well as we also have some oblique triangle problems. So let's take a look at an example. We'll go into the textbook. Here's example 1. It says the angle of elevation. It says the angle of elevation of the sun is 35.1 degrees. Now I'll give you pictures on the test, so you'll see these. 35.1 degrees. Elevation of the sun. 35.1 degrees. At the instant, the shadow cast by the Washington Monument is 789 feet long. At the instant a shadow is cast by the sun, cast by the Washington Monument, is 789 feet long. 789 feet long. Find the height of the monument. Find its height. So what we have over here, we have the Washington Monument. And here's the sun over here. Cast a shadow. And this angle here is 35.1 degrees. And it casts a shadow that you can measure this. And you say you can't get up and measure the height directly, but what you can do is you can measure this distance here. And where the shadow ends, and you get that that's 789 feet long. Okay, we know this is going to be a right angle, so it's a right angle trigonometry. Now, if we wanted to, we could figure out this angle, but we don't need that angle. What we're asked to find is this height, h. We don't need to know that hypotenuse length, but this is what we want to find, the height. So what do I know? I have various trig relations, and the one that does not involve the hypotenuse is the tangent. So the one we have for that is we simply have that the tangent of an angle theta is the opposite over the adjacent. So what we do know is that the tangent of theta, it's the opposite side over the adjacent side. So for this particular triangle, we're saying that the tangent of 35.1 degrees is equal to the opposite. That's what we're looking to solve, that height h, over the length of that adjacent is 789 feet. So a very simple calculation. I can solve for h, and it's just 789 times the tangent of 35.1 degrees. And plug that in, and plug into your calculator, and you get h is approximately equal to, plug in, make sure your calculator is set for your degree mode, 554.5 feet. And there's an estimate of the height of the Washington Monument, just by using some simple trig. Instead of having to go and measure the entire length, you could use existing things in nature and what we know about solving triangles to do that. Okay, let me give you one to try here. Give you a similar one, but slightly different, and see if you can figure out this one. So here's one for you to try over here. So now we have like a lighthouse. You might have some sort of a lighthouse. And what you are given, you're looking at a boat, some sort of a ship in the water, some sort of a sailing ship. And you're up here at the top, and you can measure your angle this other way over here. So, and say you measure this angle out to where the base of the boat is over here. And this angle I can measure. You can measure this one as well, but this angle we measure. This angle here is 12 degrees. We know that I have a height of 135 feet. Let's say we know this height over here is 135 feet. Can you tell me what the distance that boat is out away from the lighthouse? So this is what we'd like to figure out here. I'd like to figure out that distance here. That distance, we'll call it D. Okay, so try that and see what you get. If you can find that distance D. And again, we're assuming that this is a right angle right there. You can set it up and solve that. So try that yourself. Another right triangle problem. And we'll round it to the nearest foot. Does anyone want to see how I got 635 feet? Are we okay with that? Okay, so let's draw a triangle over here. I'll just take the triangle, what we do now. Put all the known information over here. This is what I don't know. That's my unknown. I know this is 135 feet. This angle here is 12 degrees, but this entire angle here is 90 degrees. So to get this angle here, I'm taking 90 degrees, subtracting 12 degrees to give me 78 degrees. So that's the measure of that angle there is 78 degrees. Okay, so what do I have? I still have that. I don't know any information about the hypotenuse, and I don't need information about the hypotenuse as long as I can bring in something that doesn't involve that. Again, that's the same thing. The tangent. So I do know that the tangent of theta is the opposite over the adjacent. Okay, now I'm going this way. So the opposite angle over here is, the opposite side is D, and the adjacent is the height. So my tangent of 78 degrees is the opposite, that's what I'm looking for, opposite over my adjacent, which is 135 feet. Then I can solve this for D. So D is 135 feet times the tangent of 78 degrees. Now let's put that on our calculator just to see that. And again, make sure you are set for your degree mode. And you can always change your degrees to radians if you wanted to, but my suggestion is to, properly set your calculator for the right mode. So here we have our calculator over here. Turn it on. Do a quick check. The mode is in radians, so we need to change that over to degrees. So very simply, it's 135. That's the height of our lighthouse, times the tangent of 78 degrees. So you get 635.125. We'll round it to the nearest foot. So that gives us a total of 635 feet then. Not too bad. Relatively simple and easy to do. My suggestion is sketch a picture if it's not given for you already. And it's going to be very easy to solve these problems. Both of these were right triangle problems. Let's take a look at another example. This is sometimes, trigonometry is used a lot in planes when you're flying distances. It's used a lot in navigation problems as well. It's a very important aspect of that. And it's also used in astronomy when you want to figure out how far certain suns are away from us, other stars are away from us. You can kind of look at that and measure angles very precisely and get a good estimate on their distances away from us. Let's take a look at another one that's no longer a right triangle, but more along the lines of an oblique triangle. Let's take a look at some oblique triangles. So, for example, we have the following. An airplane is flying from Chicago to Illinois. So I'm going from here. I'm going to go from Chicago to, say, Louisville. Not drawn in the right direction. We're just writing it this way. It's actually done in an opposite direction. Louisville is beneath it. But let's just say we flipped everything around. And we know the following is true. We know that the total distance, so now we know this distance here is 330 miles. So this is our distance. We know that's 330 miles directly from one city to the other city. And say it's been traveling for 20 minutes at an average speed, so it's traveling. For 20 minutes at an average speed of, in this case, 325 miles per hour. When the pilot notices they have been flying 15 degrees south, so they've been flying at this other orientation over here. So they're going for a certain amount of time, for 20 minutes, and then they notice that they're, south of where they want to be, that this angle here is 15 degrees. So they suddenly notice at this time, after 20 minutes have passed, that they're off course slightly. Okay, what is the angular direction? Let me go a little bit further so we can see it. So what is the angle that they now have to go in to correct for that to get over to here? So now I want to change my angle. And come to at a new orientation. So what is this angle? And what is this distance that I now have to go? So those are the things you would like to figure out. No longer is a right triangle, so we do not have anything like that. Okay, so let's kind of put everything that we know up, and we're solving an oblique triangle. So we can set it up just like we normally would, solving any other oblique triangle, then interpret it in the end in terms of the given information. So I want to find all the angles, and I want to find the length of all the sides. So let's just draw my oblique triangle over here, and we'll start labeling these over here. So we have this angle, this side. And it doesn't matter, we can call this angle, call that angle A, B, and C. So the opposite, little a, little b, and little c. We know angle C, that's given to us over here. So I can put that in over here, and that is 15 degrees. We know my length A. So I know my length A, which is 330 miles. Well, I also know this distance here, which is my length B, but I have to figure that out. Because what it is, I'm going at 325, so I'm going 325 miles per hour for 20 minutes. So how far do I travel? Well, this is in minutes. I need to plug this into hours, so that's essentially 1/3 of an hour. So I can change my minutes to hours, so I get 325 miles per hour. 20 minutes is 1/3 of an hour. So the hours cancel out, and that just gives me 325 over 3 miles. So I just plug that in and get an approximation for that value. So 325 divided by 3 gives me 108 1/3. So let's just say my length B is 108.3 repeating miles. I think that's it. Yep, okay. That's all the information I know. I know 3 pieces of information so I can solve that triangle. Okay, so now that I did that, why don't you try it? See if you can solve that triangle. What can you do to solve that triangle? The thing we can do is, notice I don't have, like 2 pieces of information for A or B with C to be able to solve that. So I have to find length C, which I'm actually calling that D over here. So how would I do that? Law of cosine. So see if you can estimate C using the law of cosine. So try that yourself. Once we set it up this way, it's fairly easy to kind of take a look at that. So the law of cosine, let me put it up there just so you kind of remember this. approximately, we'll go to the nearest mile then. 227 miles. Approximately. It could be off by a little bit. Does anyone want to see how I got 227 there? Okay, just plug everything in. So here is my c squared is equal to a squared, so I take 330 squared. I'll round this to 108 plus 108 squared. It's an approximation anyway. Minus 2 times 330 times 108 times the cosine of the angle 15 degrees. So I get c squared. Just plug everything into your calculator. Let's just do all the complicated calculation. My calculator is now already set for my degree measure, so I don't have to change that. So I come over here, let's see, turn it on. So c squared is equal to 330 squared plus 108 squared minus 2 times 330 times 108 times the cosine of the angle in question, which is 15 degrees. So that gives me 15. Did I do that correctly? Yeah, so I get 51,712.8. That's my c squared. So I have to take the square root of that. I'll put that whole thing in. 51,712.8071. And I get 227.4, which I'll just call 227. Yeah, if you maybe you included the extra 0.33 for the 8, maybe you got something closer to 228, that would be okay and acceptable as well too. Hey, Colin, do you have a question? You have your hand raised there.
Yeah, I got
What's that?
0.89. I got 217.89.
Dude, did you put 330, 108?
I did 108.
Okay, so yeah, so that would be fine too. If you did 0.3, that's close enough. It's going to be within reason. So, yep, you can. So you approximated that, and let's see. Let's do the 0.33. Let's see what we get over here. So if we do the same thing, say we do 330, square that one, 108 point, and let's put a few of these in. How many do you want to put there? Square that. Minus 2 times 330 times 108.23. 1, 2, 3, 4, 5, 6. Keep it consistent times the cosine of the angle across from them. And I get this 51,572. So I take the square root of that. 51,572.41467. I get 227. Still, you know. Yeah, so you can do all the same thing. So maybe, I don't know, maybe Colin, you might have, look at back, you might have hit something slightly off or something like that. Because it should get closer and closer, it looks like, to that 227. But if you want on a test, let me tell you, on a test, I want you to show your work, if you will. So where are we back here? Okay, so on the test, make sure you show your work. I got 227 either way. Okay, now we're not quite done yet. We know how far we have to go, but we don't know our corrective angle over here. Meaning, we would like to find this angle A over here. So what can I do? Well, I'll use these pieces of information. I know two things about C and one thing about A. For that, I could use the law of sines. So why don't you try that? Try the law of sines and see if you can estimate angle A. We could find B easily enough in the end, but we don't really need that angle. But I want to find this angle A. We're not done after that either. So try and estimate that angle A. That's going to be a little bit difficult because remember the sine. We have some problems here. You got to be careful of that because the sine. Notice this angle here. This angle is greater than 90 degrees. I'm going to be doing the arc sine, but the arc sine is not good for anything greater than 90 degrees. This one's a little more involved, the oblique triangle. So see if you can estimate angle A for me. Then I'll go over that. So try it on your own and then see what happens. Again, we'll get an approximation over here. You'll get 22 degrees, but remember there's two possibilities with your sine. And you have your angle on a unit circle. Is one over here at 22 degrees, and a similar angle at that same value over here at 158 degrees. All they do is I subtract 22 from 180, and that gives me my other, that's 22, so that's 158. Does anyone want to see how I got 158 for that sine? The angle A. Is that okay, using the law of sines? Is everyone okay with this? Does anyone want to see that? Everyone's okay? Not too bad? Okay, so we know this angle here. Now we have to answer the final question over here. What we got here is we actually got an estimate for this angle here, because that's 158. So now you have to go 22 degrees this direction. So that's my answer over here, is that this angle here, is I'll have to shift 22 degrees. And the distance I now have to travel is 227 miles. So I'm a little bit off course. I went 108 this way, so it's going to give me 335 miles. So I'm going 5 miles extra in my trip. Because I went 108.3 and then 227. So of course, used up a little extra time and gas to get that, and fuel to get that. So that's how you can solve, some realistic problems using the solving a triangle, techniques we were looking at. But any questions on that? Yes, Ashley.
Sorry. So when we looked at the 158 degrees, did we choose that angle because we're looking at it and we know it's more than 90 degrees? Well,
yeah, it has to be. You're asking yourself, anytime you use the arc sine, it's always a question of, is there another angle that'll satisfy that? Because the sine only goes from arc sine only goes from -90 to +90. That's its, range. So you always have to be cautious about, is there another triangle that would work for? there is one that does work for the 22 degrees, but is there another one that works? And the other angle is 158. And then you look at it and say, well, I know this is 108. I know this is 227, so that angle has to be greater than 90 degrees. Because we already found the 108, and we already found the 227, and that's 330, so we know it can't go the other way. The other possibility would be this side would have to be much longer. If this was 22 degrees, then my side of B over here would have to be much longer. It might be, 300 or so miles or something like that. So again, you have to look at your triangles, just like you did when you were solving the triangles without this physical material. You say, is there another triangle? Because there's this triangle that would exist, but there's also another triangle that would exist over here, and this A over here would be 22 degrees as opposed to 158 degrees. So this length here would be much longer than the 108 that we found previously. Because this could still be 15 degrees, mind you, and that could still be 15 degrees, but from this angle here, it touches in two different places. So that's another case where you have to look for that second possible triangle.
Question like this, would we have a picture or would this be something we have to draw? Because I could see myself messing this up and looking for the bigger angle.
On these things I do give you the pictures. But in the real world, you should start being able to, okay, can I construct the picture myself? But I'll give you the pictures on the test. Make it a little bit easier for you at this level. But eventually, if you go to another course where they want you to pull it all together, we're focusing mainly on the mathematics here and how to do it. There, they'll teach you how to set it up more appropriately. But you should get reasonably proficient at setting it up. And draw the pictures, draw the triangle. I can see the train of thought going to see what you may have gotten incorrect, so you can get partial credit if you make a mistake. Like, someone made a mistake and got 217. I can see where the work is. You may only lose, and as long as you did everything else correctly, you may get most of the points there. You may only lose a little bit for not entering it incorrectly. Sometimes the mistake is as simple as people not having their calculators set for degree mode here. So sometimes that's a common mistake over here. You don't have degree mode, you have your radian mode set in, and it messes it up. Any